So we're going to go through this process storyboard, right? And this is what you guys would have done in the fab had we not shut down for Corona coma. Okay. So the process, we developed it way back when I used to be at CNM, and the grant started there. We had collaboration with UNM. So we developed the process at that time, and then we've improved upon it over the years, but this is pretty much the core process. Of course, you need to incorporate some kind of methodology from taking a environmental pressure change and converting it into some kind of electrical signal so that you can do processing on that electrical signal. Okay, so a Wheatstone bridge consists of 4 resistors. Usually one of the resistors is variable, and then your output voltage will vary depending on the change in that resistor, its resistance. Okay, but we actually use 2 resistors, variable resistors, because then we get twice the effect. Okay, and typically you can use different materials depending on what you're doing. So we used chrome and gold, right? Chrome is put down so the gold will stick to the silicon nitride, and we'll get more on that later. And it looks cool. So, but now we can use nichrome or just chrome, and we've done copper. So there's different materials you can use, and and evaluate to see which works best for whatever application you have. Gold is nice because it's pretty inert, doesn't react with chemicals very well, so it can be exposed to the environment a little bit better. But it's fairly conductive, so its change in resistance as a function of stress isn't as much as you would get out of nichrome, for example. Okay, so you can see the Wheatstone bridge circuit, right? That's the gold part, and then you can actually see the membrane itself that the circuit is sitting on top of. Okay. So how do we determine a change in pressure? Well, if you look at the side view of this device, you can see you have a very thin membrane, and then on top you see this little circuit right here. It's been cut across. So this is a thin metal lead, right? This is your variable resistor, for example. Okay, you have a cavity underneath, right? So usually this cavity is sealed. So it's usually around, atmosphere pressure or sea level pressure. And then that way, if you have a change in pressure on top, if it gets higher than what's in the cavity, it'll go down. If it gets less, it'll go up. Okay. So as the membrane deflects, the resistance will change in the variable resistor. And then you have to apply a constant voltage, right? So your output is kind of related to the voltage you put in to it, right? And we've done 3 volts and 5 volts and whatnot, and it just depends what range you want the output to be in, and then what the resistors nominal values are, and then how they change with the change in pressure. Okay, so to make the electronic circuit, we need metal, and in this example we're using chrome and gold. And then the membrane is going to be made out of silicon nitride. And then the reference chamber is actually an etched chamber that's in the silicon, crystalline silicon wafer substrate. Okay, so how do you make bare silicon wafers, right? Well, there's a process that's used. You take pure polycrystalline silicon that's been refined down to 99.99s purity, because you don't want any impurities in it, and that's where the trick is. And if you can get it that pure, then you melt it down in your crucible, okay, and you heat it up to about 1400 to 1500 degrees Celsius so it melts. I think the melting point of silicon is about 1470 degrees C. So you take it to the melting point. Once you get a melt, then you can put a seed crystal on the end of a rod and dip it into the surface of the molten silicon. Then you slowly pull it out. Okay, and you can see that the crucible typically will rotate in one direction, and the silicon ingot, i.e. the rod that the seed crystal is on, will rotate in the opposite direction. And you pull it out really, really slow. So the seed crystal determines the crystal orientation of your wafer. Okay, so they have to do some X-ray diffraction on the seed crystals to determine the seed crystal orientation, and then they know how to mount it on the end of the rod. Okay, so thickness of the wafers range. 4-inch wafers are usually around 520 microns or so, and 6-inch wafers are a little bit thicker. They're up around 620. And then as the wafers go to 8-inch, they get even thicker. And that's so they're stiff enough that, that it doesn't break. So someone's got a chat question. How do they make the seed crystals? That's a great question. Well, if you make polycrystalline silicon, right, that's a grain. Then you'll have different grains in there. And typically what they'll do is they'll use a small grain and create a larger crystal based on that. And then they'll determine the orientation of that, and then they'll break up that larger crystal into smaller pieces that are used as a seed crystal. Okay, good question. All right. And sometimes we dope the substrates, so they have some properties, some electrical properties. So you'll have N-type and P-type doped silicon wafers, and that's to aid in the making of transistors. Okay. Yeah. So once you create the ingot, which is actually just a huge silicon crystal, you slice it with a diamond saw. So this saw depicted here is an actual saw blade with diamond encrusted edge on it. That's the older way of doing it. The newer way now is diamond encrusted wire. So they actually use a wire to cut through this. And that way they can make the cuts thinner. And as an engineer, you know, you can think about, why would you make the cuts thinner? Well, you get more slices per ingot, right? Per linear foot of the ingot. And of course, once you cut the slices from the ingot, the surfaces are pretty rough. So you have to do some polishing and lapping. Okay, so they use chemical mechanical polishing, very similar to what they use for making DRAMs when they polish the insulator materials between layers to reduce the topography. They use the same sort of process to polish and lap the bare silicon wafers. And typically the front side, one side of the wafer, we call it the front side, is very, very smooth, and that's the side you build everything on. And the back side tends to be less polished, kind of rough. And there's a couple of reasons for that. One is polishing is expensive, so you only polish the side you need polished. And then the other reason is the back side's a little rougher, so it acts as a gettering. So impurities in the processing get stuck on the back of the wafer rather than tending to stick to the front of the wafer. Okay. Sometimes you use double polished wafers, so double side polished for specific applications. But typically, the only time we used them in industry was when we were checking flatness of our chucks and things like that in lithography. So we wanted an extremely flat wafer. So that would translate any variation of the chuck that the wafer's sitting on to the surface, and then we could measure the variation of the surface of the wafer, which is translated from the chuck. Any questions on polishing? Not seeing anything in the chat box. I guess we're good. Okay, bare silicon wafer, you've all seen that. That's kind of what it looks like. Now, what is the grain size for polishing? Oh, that's a good question. It's very fine. It's very fine. I'd have to look that up. They usually use a couple different grit sizes. So they'll have a larger grit to get most of it polished down, and then they'll use a very, very fine grit. So I'm assuming it's down in the, you know, tens of nanometers size of grit to get that smooth surface. So that's a good question. So this is what a bare silicon wafer looks like. You know, this looks like it's on the back side of the wafer. It looks a little rough. Okay, it's not shiny. The polished side of the wafer would look like a mirror. Okay, so the first step we do once we have our wafers is we put silicon nitride on the wafers, and that's done with silicon nitride deposition. We use a low pressure chemical vapor deposition process. So that's LPCVD, low pressure chemical vapor deposition. And we deposit about 1 micron thick of low stress silicon nitride. So it has to be low stress. If it's high stress, then, you know, the wafer itself will look like a potato chip after the processing because of the stresses vary, right? So remember, when you deposit these kind of things in a furnace, they deposit at high temperature. So now you've got a film on top of a silicon substrate, and then you cool it down and you take it out of the furnace. And if your thermal expansion coefficient is radically different between the substrate and the thin film you put on there, it'll cause some stress, and you can actually get the wafer to start to look like a potato chip, right? And of course, any structures you make out of the silicon nitride will be stressed, and then you'll see curved cantilever beams, for example, or distorted pressure sensor membranes. Okay, so there are special processes that ensure that it's a low stress result. And right now we're getting our low stress silicon nitride wafers deposited at Arizona State University's clean room. Okay. So this cartoon shows you a little bit on how it's done. So we need a source of nitrogen and a source of silicon to do silicon nitride. So the nitrogen source is ammonia, NH3, and the silicon source can be silane. Sometimes they use dichlorosilane. So there's different gases you can use that will bring you the silicon. And then once it goes into the furnace and gets heated up, the silicon or the silane will disassociate from separating the silicon and the hydrogen. Likewise with the nitrogen and the hydrogen and the ammonia. And then the silicon nitride will combine and deposit onto the wafer. Okay. Any questions on that? Okay, 2 layers of different materials like a bimetal thermal strip. Exactly. Yeah. Yeah, so the older thermostats in your house, mechanical ones, where you could see the temperature reading from a needle, that's a result of a bimetal spiral spring that relaxes and contracts as the temperature changes, and it moves the needle back and forth. So yeah, the old school mechanical thermometers or thermostats were like that. Now we have, you know, typically some kind of digital system. Joshua asked, is most polishing universal across the wafer? Let me see. Or are there specific polishes for certain applications? Yeah, you can get highly polished wafers that are super flat. So we usually have a flatness specification, right? So they'll have, you know, how flat it is overall over the whole surface of the wafer, and then how flat is it across a small section of the wafer, right? And that deals with how well you can do your photolithography. So you want a flat surface if you're imaging something onto it. The smaller the structure you image, the flatter that surface needs to be. So yes, you can get different grades of wafers, different flatness grades. And of course, you pay more for them, right? Oh, good questions. Okay, so after the silicon nitride deposition, right, depending on the thickness, you'll get different colors. So this shows that the wafer has something on it, okay? Just by looking at the picture, you can't really tell what's on there, but it's actually silicon nitride. Okay, and the thickness makes it look a little green at this angle. All right, so then now we've got our wafer substrate, we've got our silicon nitride, and it's on both sides of the wafer. Remember when we do the low pressure chemical vapor deposition, it deposits on all sides of the wafer, front and back. Okay, so now we've got to make a pattern on the back side of the wafer, because we're going to make our chambers. If you remember that first slide where we showed the cross section, we've got to make holes in the back of the wafer so we can etch out the chambers. Okay, and to do that, we've got to coat the wafer with photoresist, but we also want to coat the front side of the wafer with photoresist to protect it. Okay, so this is a double process. So we typically coat the front of the wafer, and then we bake it, right, to remove the solvents. You remember that from our lithography labs. And then we flip it over and we coat the back side of the wafer. All right, and then we pattern that. So that's essentially what we do. So we do our front side coat, okay, and then we bake the wafer for a couple minutes, and we cool it down, and that gets rid of most of the solvent. And these specifics on the processes vary depending on what photoresist you end up using and all that. So they've varied over time, but this is a good place to start. And then we used to deposit HMDS with a pipette, so you can get liquid hexamethyl disilazane rather than vapor prime, but you could do it either way. And then we dispense, do the backside coat, okay, and we again have to do HMDS so the photoresist sticks. HMDS, as you know, is hexamethyl disilazane, and it acts as a primer. And then again, we bake it. So the pictures there show you what the corresponding steps are related to the coat parameters. So Jens has a couple of questions. Isn't there a chance to damage the photoresist on one side? Yeah, absolutely. The whole purpose of putting photoresist on the front side, you're not going to be processing on the front side, but it's to protect the front side so it doesn't get scratched up. So we're using the photoresist as a sacrificial layer. Okay, so it's sacrificed. All right, so we coat the front of the wafer, and then we flip it around, coat the back of the wafer, and that's where we're going to do the patterning. So the back of the wafer is going to be up through this process step. Okay, hopefully I answered your question there. Muriel has a question. Step 4 and 7, thickness of HMDS doesn't matter here. Remember, hexamethyl disilazane is a monolayer typically, so it's one molecule thick. Okay, so you can dispense it with liquid. You spin it on, right, and it'll evaporate, and one layer will remain on the wafer typically. Okay, now the way we do it now is we use an HMDS oven, and we use a vapor. So you only get a single molecule thick layer. So it's a monolayer. Okay. Remember, the HMDS is only there so that the photoresist sticks to it, and we keep water off of the surface of the wafer, because if water gets a water vapor layer gets on the wafer, then the photoresist has a tendency not to stick very well. And that'll give you problems later when you're processing. You'll get what's called an adhesion problem or a lifting of the photoresist. And you can actually lift pattern structures off before the etch right? So then you get a bunch of defects. Okay. So, you know, backside coat looks about the same as that other wafer. I can tell it's coated because you've got the tweezer marks here, right? You know, our tweezers damage the photoresist. That's why we only use the tweezers on the edges. Okay, and now we've coated the front, we've coated the back, right? Front is first because that's going to be front side down, shiny side down, and we're going to pattern the back of the wafer. So that's the second coat. And we put it in the exposure tool, which is our Carl Zeiss, which is a 1X mask aligner. Okay, and the mask you see on the right, so one of our older masks, and it's just a bunch of holes for the chambers. And we've also have some streets in there for dicing purposes later. Okay, and I'll talk a little bit about that probably in another lecture. So typically what we do is we put the mask in the Carl Zeiss. You guys are very familiar with that. You've done lots of photolithography. Then you load the wafer and then you expose it. So this is 9260 photoresist, which is thick, 6-7 microns thick or so, maybe a little more, depending how fast we spin it. So it needs a lot of photons to expose it, right? So we expose it typically for 300 seconds, which is like 5 minutes, right? So that's a lot of exposure. And if you remember, it's 3 milliwatts per square centimeter is the intensity. So if you multiply 3 by 300 seconds, that'll give you the millijoules. So it's quite a bit of millijoules to expose this thick photoresist. Okay. And the reason we need thick photoresist is because the etch is pretty tough. And it'll chew up the photoresist and the silicon nitride at the same time. Okay, so that's a close-up of the photo mask. Okay, so you can see there are 4 chambers for each chip, and then the lines in between are scribe lines. So in this design, we didn't have a dicer, so what we did was we etched lines into the back of the wafer, and then when we did our KOH etching, it would etch down and allow us to be able to break the chips apart at the end of the processing. Okay. All right, now we're gonna we've exposed the back of the wafer, right, with lithography, and we go ahead and develop it. And you guys are familiar with it, but I'm gonna just review it again. So we have to wear proper PPE, personal protective equipment, whenever working with chemicals. So you see the face shield, the triple trionic acid gloves, and the acid apron. And this is so we don't get anything on our skin. This is a base solution. We're going to use AZ400K 1-4 developer. It's a potassium-based solution, but it's a base, right? So we place the wafer in the Teflon boat, okay, and then we pour developed solution into a container, insert the boat so the entire wafer is submerged. So that's a batch process. So that's one way to do it. We can also do it in Petri dishes, right, individual wafers at a time. So it depends where you work and what you're doing, how you develop it. Okay, once it's developed, and this develop takes a long time because the resist is thick. We take the wafer out and we do a quick dump rinse, right, QDR, and we do it 5 times. So that gets the developer off. It stops the developing process immediately, and we use deionized water for that, right, because we don't want any contaminants in there. And then we do a spin rinse dry, right, to dry the wafers off, okay? And we monitor the resistivity of the water coming out of the dryer. And so we want it to reach 15 mega ohms, which means that the water is pretty clean, okay? And then we do a microscope inspection to make sure we actually completed the develop process. If we have areas that haven't been developed, we can go ahead and put it back in the developer for a little more time. Okay, so when we're done with the backside developing, it'll look something like this. So the lighter squares is where we've developed out the photoresist, and the darker regions around it still have photoresist on it. Okay, so that's what it looks like. Now we get to etch it. So we do reactive ion etching. So that's that uses carbon tetrafluoride, I believe. Oh no, carbon hexafluoride. And that's the main gas. You put it into an RF environment, it disassociates and it glows. So radio frequency causes the plasma to be created inside the chamber, similar to the plasma you see in fluorescent light bulbs. Okay, and we usually etch for about 300 seconds, and then we rotate the wafer 180 degrees and etch again, and that's to make sure that the etch is uniform, because the plasma isn't necessarily a uniform plasma. So by rotating the wafer 180 degrees, you can get rid of some of that uniformity issue. Okay, so I'm just going to do an overview on that. So after you etch it, it looks like this. So we still got some photoresist on there, but we've etched through the silicon nitride. You can see that the squares look grayish. So that's what the back of the wafer looked like. Okay. And then we got to take that photoresist off, whatever's left. So, you know, we can use photoresist stripper, or we can use Piranha, or we can use acetone. So there's different ways to strip it. We used to use Piranha, that's the industry standard, and it leaves you with a very, very clean surface. But we found using acetone works pretty well too. Okay, so in this scenario, we're using Piranha. So that's sulfuric acid and hydrogen peroxide. So we can actually do it in a bath and do a bulk etch or a bulk strip, or you can do it in beakers. Okay, so you can imagine sulfuric acid and hydrogen peroxide, they will chew up organics really well, and they strip a lot of things like metals, trace metals, and that kind of thing off of the surface. So it really cleans the surface well, and we typically do it at high temperature. High temperature makes chemical reactions go much faster. Okay, but of course, if you get this on your skin, it's a very highly caustic material, so it will burn you very badly chemically, and since it's at temperature-wise as well. So you got to be very, very careful when working with these kind of things. Okay, so again, proper personal protective equipment is required. So after we take the photoresist off, right, it looks like this. So you can see where the silicon nitride is remaining and where the silicon nitride has been etched away. And that's exactly what you want to do, right? So we do this a lot in semiconductors and in MEMS fabrication. You know, you put a material down, then you put a photoresist down, you pattern the photoresist, and you etch away whatever's exposed, and then you remove the photoresist. So that's a common set of process steps. And you build layer upon layer upon layer upon layer until you get your final device created. So now we're going to do the front side. So we got the backside chambers defined, right? Patterned. Now we're going to do the front side. Okay. The front side consists of, again, coating the wafer again, but now we're only going to coat the front. We're using a Liftoff resist followed by a regular resist. Okay. So in this scenario, we're using LOR. I think we typically use LOR 5B. So if you want to look that up, Microchem produces that. So if you just do a Google search on LOR 5B, you can get a lot of information on that type of material. So we put a thin coat of LOR 5B, and then on top of that, we put a coat of AZ5214. Okay, and we can use other photoresists as well. All right, and so now you've got two layers. One's a liftoff resist, and one is a photoresist on top of it. So this is where it gets pretty cool. So there's the front side photolithography coat. Okay, so now remember, we have a liftoff resist underneath a regular photoresist. That's photosensitive. Okay, now we go ahead and we expose it again in the Carl Zeiss. We have to, do we bake in between coats? I don't think the LOR requires a bake, but I could be wrong. Let me think. Yeah, we might, I think we do. I think we do a short bake on the LOR. And then we put the photoresist on top of that and bake that. Yeah, because we have to get rid of the solvent. All right, so we go put it on the Carl Zeiss again, and we expose it, but this time only for 40 seconds. And the other thing we have to do is we have to align the Wheatstone bridge pattern to the holes on the back of the wafer. So included in the mask are alignment marks, and they're typically they're like 4 squares or a cross, and the cross fits inside the 4 squares. So the back side would have the 4 squares, and the front side mask would have the cross, and then we have to align the front to the back. Otherwise, when you etch your cavities and create your membrane, the membrane will be misaligned with the circuit. So that's what you see in the TV screen in the lower right figure labeled 3. So you can see the structures there, and they're being aligned to the structures in the back. Now in this case, they're actually aligning the Wheatstone bridge structure to the holes that are patterned on the back to make sure they're all lined up. And it's a really cool process. You basically find the marks on your wafer that are on the back. So you rotate the wafer around until your microscopes see the 2 marks on the back. Then you capture that image, and then you go to the top view, okay, and you align the mask to the wafer by moving it around. So it's a kind of a tricky process, right? But when it's all said and done, you can align the top to the bottom. And I'll have to show you guys that in reality because it's a little tricky. Maybe we'll make a YouTube video on that someday in the future. All right, so this is what the front side mask looks like. Okay, so this is yeah, this is the Wheatstone bridge pattern. So let's continue on. So we pattern the Wheatstone bridge. We make sure it's aligned to the backside pattern. And then again, we have to go through the develop process. But this is where the nuance is, okay? As we're developing through the photoresist, it goes straight through the photoresist only where it's been exposed. Okay, so we expose the areas that we want to have developed out. Okay, then once it breaks through, right, if you can look at the lower left picture, once it breaks through the photoresist, it starts developing the liftoff resist, but in 2 directions. So it develops underneath the photoresist. So the liftoff resist doesn't have any photoactive compound in it, right? It only purpose is to provide a spacer and allow you to develop out underneath the photoresist so you can get this overhang. Okay? So timing is important here in the develop side. If you don't develop long enough, you don't get that overhang. And if you develop too long, the overhang could be so big that the photoresist, the smaller structures will lift off and float away. Okay? But notice now we got holes in the photoresist. And then we have the hole is open to the silicon nitride underneath. Okay? So that's the key there. And then of course you quick dump, rinse it, spin, rinse, dry it, inspect it, make sure that it's been developed properly. Okay, and then and now you have a patterned wafer. So this is what's really interesting. If you look closely, right, the openings is not photoresist, right? These are openings in the photoresist, bond pads and the actual wheatstone bridge structure. So we're not going to protect anything that's underneath. We're going to leave it open. Okay. And then we have to do some deposition of metal. Okay, so what happens here is we deposit the metal in an evaporator in this case. You can also use a sputter tool, right? We've moved on to using a sputter tool instead of an evaporator, but you know, evaporators are cheap, right? And you can have evaporators that can do 18 wafers at a time. So you might want to use an evaporator if you're in high volume production, right? Sputter tools, typically single wafers at a time. That's really good for R&D. You have a lot more control over the deposition. And you can do alloys and do weird things that you can't do in a evaporator. Okay, so in this case, we're going to deposit two metals. The first metal is chrome. So chrome will be deposited onto the wafer. And chrome sticks to silicon nitride really well. That's why we use chrome first. Chrome sticks to silicon nitride really well. And then after the chrome deposition, we deposit gold. And we have to do this one after the other in a vacuum. If we do chrome and we take it out, you get a chrome oxide forming. And then when you try to put gold on it, it won't stick. So gold sticks to chrome really well. Chrome sticks to silicon nitride. Gold does not stick to silicon nitride. Okay, so you always have to do this chrome followed by gold. And the end result is what you see in the lower right corner there. And there you see your wheatstone bridge that's basically photoresist that's been coated with gold and openings that have been coated with gold. So these openings here, okay, have gold stuck to the silicon nitride. This gold here is stuck to the photoresist. Okay? The reason you see these black lines is the light doesn't reflect from vertical structures back into the microscope. So it's a well-defined edge, right? Remember, you have those little T-shaped things. So the gold is on top, it's a little bit on the side, and then it's on the bottom on top of the silicon nitride. Okay? So the edges appear to be black, right? Because they're vertical structures. You're not getting any reflected light back into your microscope. So it's always good to try to understand, well, why do I see the edges? They got gold on them, but they're facing in a different direction. So when the light hits it, it goes out. It doesn't come back up through the microscope. Okay, so now you can see you have a very well-defined circuit. Okay, but we got gold everywhere. So we got to get rid of the gold that's sitting on top of the photoresist. Okay, so we've done the deposition. The wafer looks like this. You can see the structures because of the edges, because they're vertical. Okay, now we got to do what's called liftoff. And liftoff is a cool process. So you can use acetone. Acetone will dissolve your photoresist. Okay, so now you can see what's happening. This is at time 0 and this is at some other time. Okay, and you can see the photoresist is being dissolved away underneath the metal. So those parts are going to lift off and float away. Okay, it's not going to affect any of the gold and chrome that's sitting on top of the nitride, the silicon nitride. All right, now the funny thing is acetone doesn't dissolve liftoff resist, so that'll stay behind. Okay, so when you put this in a beaker or in a dish, right, with acetone, you can see those areas lifting off and floating away. And then as the longer and longer you leave it in there, the better the liftoff is. And then you eventually rinse that off with acetone, and you rinse it again with methanol or isopropyl alcohol. And then you do a water rinse and spin rinse dry. And then you end up with what's on the right. So now we've got a beautiful wheatstone bridge stuck to silicon nitride. Okay. Any questions on the liftoff? All right. And that's what it looks like. It looks beautiful, right? Nice gold, shiny. You can see the wheatstone bridge really well. You see there's some photolithography problem here. This structure on the third one isn't quite right, but overall it looked pretty good. Now we need to get the liftoff resist off of there. We got the photoresist off. Now we need the liftoff resist, and that's really easy to do. We do it in a solution of developer. If you remember from the develop stage, the liftoff resist dissolves in developer, but you don't want to leave it in too long. Now you can put it back in and get rid of it. Okay. So we do the liftoff strip. Okay, and get rid of it. So we submerge it not in potassium hydroxide, but we submerge it actually in developer. Okay, and now, now the liftoff resist is off of there. We just have gold and chrome stuck to the front side of the wafer, silicon nitride. So we're good to go. Now, this is one of the last steps. We're going to actually make the chambers. Okay, so we have to etch it in potassium hydroxide. All right, and you can also use sodium hydroxide. Sodium hydroxide is drain cleaner. You can buy it at Home Depot, right? Pure sodium hydroxide in powder form, and then mix it with water. We actually purchased potassium hydroxide already pre-mixed at 45%, and then we dilute it down to about 25%. Okay, the thing about potassium hydroxide, it etches crystalline silicon, but it does it in a really cool way. It etches the 100 plane of silicon really fast, and it doesn't touch the 111 plane. So that's how you get the characteristic, upside down pyramid shape when you do the potassium hydroxide etching. Okay, and it typically takes about 2 hours or so to do it. We usually go at a high temperature for a while, and then we back off the temperature as we get close to getting to the membrane. If you leave it at high temperature, there's a lot of cavitation and stuff, and you can blow all the membranes. So, you get close, you still have some silicon there, and then you finish it off with a much slower etch, less robust etch with less cavitation. Okay, so you'll learn to do that as an engineer when you're developing processes, right? You want to do it fast, but then sometimes if you do it too fast, it causes more defects. So you have to balance it out. So once we're done with the KOH etching, we do a really soft rinse, right? And then we dry it with a nitrogen gun, very soft flow of nitrogen to dry it off. So we do a water rinse typically, and then a acetone rinse, right? And a methanol rinse, and then you can dry it with your nitrogen gun. And that way you don't leave too many defects behind. Now, if you look at the picture down at bottom where it says a good KOH etch, that's what it looks like. And notice we aligned it really well. That wheatstone bridge is right on top of the membrane. Okay. And then if you leave it in at too high a temp, right, you can actually blow the membrane, and you can see little shards of silicon nitride on the outsides of it. Here's what's left of the wheatstone bridge. You can kind of see the circuit metal bent up, right? So we blew out the membrane. Okay. And then you see the cavity before and after etching. And you can actually see the silicon nitride window here, and then how it etched. Okay, and that's what it looks like. So, you know, this is really nice. These slope sides are the 100 plane of the crystalline silicon. And then if you zoom in on it, look at it top down, you can actually see the membrane, right? It's a polycrystalline structure, okay? And then you actually see the Wheatstone bridge resistors on top of the membrane. Remember, we're looking from the back of the wafer to the membrane. And then you might think, oh, this is kind of an interesting crystal etch. This is an optical illusion. I refer you back to the right side picture. This is what it really looks like. Okay, since these surfaces are very reflective, it's like a house of mirrors. You got two mirrors at an angle to each other, right? And then the light reflects funny, and when you look at it in a microscope, it kind of looks like you have this bizarre structure here. But that's, like I said, an optical illusion, and you can convince yourself of that when you're looking at structures on the microscope by tilting the wafer a little bit. Sometimes you can tell that way, or try different illumination schemes on your microscope. And then when you're all done, see, now we're all done. We got a bunch of wafer, or a bunch of pressure sensors on a wafer. We want to test them out. So we can use a probe station. This is an older one we used to use. Now we have a slightly better one. But you can measure resistances and voltages and that kind of thing, and apply different voltages and see the membrane flex. The reason you see it flex is if you put enough voltage on it, these Wheatstone bridge resistors actually act as a heater and will heat up the membrane, so it wants to expand, and you can actually make it an actuator. So not only is it a sensor, but you can also use it as an actuator, as a pump, right? Flexible pump. So yeah, so that's what we were going to do in the lab. And like I said, you guys can join us when the Corona coma is over, and I can go through it with you. It'll take about a couple of days, maybe like 10 to 12 hours to do all the processing. Okay, so this is what it looks like from the top view. I showed you the bottom view earlier. Right, here's your gold resistors. Okay, and it's pretty well aligned, right? It's a little bit to the left relative to the membrane. You can see the outline of the membrane here, but that's pretty good for aligning it from the back side to the front side. All right, and then these are the acknowledgments. So we got National Science Foundation funding to do this, so I always want to give them thumbs up for allowing us to do this over time, and these educational materials are utilized for technician students and their instructors, as well as engineering students and their professors. So I think that's about it for us. Yep, that's it. You guys have any questions?